With the Big Bang itself, it was an equal competitor to the steady state theory.
It's been more than 100 years since Einstein changed how we think about time and space. But how does it really work, and what does it mean? Time and space appear incredibly familiar and straightforward, part of our everyday experience, but they're hiding a lot of questions we don't have answers to. Einstein's ideas started to answer some of them, like what space is made of and if time is real or not. But the more we dig into these questions, the more mysterious time and space become. This is Reveal the Mystery. If you are curious to learn mysteries of the world, space and beyond, consider subscribing. In March 1949, the British astronomer Fred Hoyle made an appearance on a BBC radio show where he discussed various theories concerning the universe. Hoyle held a belief in the steady-state model of the universe, which posited that the universe had neither a beginning nor an ultimate conclusion. It perpetually existed. However, an alternative model had been gaining traction over the past few decades, one that suggested the universe did indeed have a beginning, originating from a minuscule point and subsequently expanding outward, a process that continues to this day. When referring to this concept, Hoyle somewhat casually dubbed it as that Big Bang notion. Astronomers were aware of the expansion of the universe way back in 1912. They figured this out when Vesto Slipher looked at a spiral galaxy and saw that it was moving away from us. Later, scientists like Alexander Friedman and Edwin Hubble added more evidence to this idea. But it wasn't until 1931 that Georges Lemaitre came along and said, wait a minute, if the universe is getting bigger, that means it used to be much smaller. If we go all the way back in time, it would have been incredibly tiny. This tiny starting point means the universe must have had a beginning. So, in simple terms, scientists gradually realized that the universe is expanding, and this led them to believe it had a definite starting point, even though it might sound a bit strange at first. As our telescopes got better, we could see really far back in time, to the very first galaxies. This helped prove Georges Lemaitre's ideas more and more. But here's the surprising part. Most scientists didn't fully accept the Big Bang theory until the 1980s. And even though it's widely accepted now, it's still a bit complicated. Some people still believe there might be an alternative explanation for how the universe works. And one of these ideas is called causal set theory. It's pretty solid when it comes to the math, and it could help us understand many puzzling things about reality. In the world of physics, there's a divide between two big theories. One is called quantum mechanics, and it deals with how particles and forces work on a very tiny scale, like atoms and electrons. The other is general relativity, which is all about space, time, and gravity. The tricky part is that these two theories have different rules, and scientists have been trying for a long time to bring them together. Now, there are 4 fundamental forces in the universe: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Of these, gravity is the odd one out because it doesn't seem to be carried by a particle, at least not one we've found yet. So scientists have been searching for a theory that combines quantum mechanics and gravity. They really want to figure this out, especially when dealing with super intense places like black holes or the Big Bang, where general relativity starts to break down. Over the years, physicists have tried different approaches to solve this puzzle. One of them is quantum loop gravity. In this theory, space-time isn't smooth, but is made up of tiny, discrete chunks. Imagine zooming in on space-time, and instead of a smooth flow, it's like jumping from one little space-time pixel to another. Time doesn't flow continuously, it's more like a series of quick ticks on a discrete clock. Causal set theory builds on this idea. Another approach is string theory, which suggests that everything in the universe is made up of tiny vibrating strings, even smaller than atoms. These strings vibrate, twist, and fold in ways that create everything we see, from particles to gravity. In causal set theory, space-time is also made up of tiny pieces, but they're called events. These events are connected through cause and effect relationships, like a chain reaction. Imagine dots on a piece of paper with lines connecting them to show which event causes the next. This lattice of connections is called a causal structure. Of course, when you're dealing with the tiniest parts of space-time, you have to use the smallest measurements we know of, which are called Planck length and Planck time. So in simple terms, causal set theory suggests that space-time is made of tiny, discrete pieces, and these pieces are connected through cause and effect relationships, sort of like a chain of events. It's another way scientists are trying to understand the fundamental nature of the universe. So, what does all of this mean? Well, it essentially suggests that singularities, those weird points where everything seems to go crazy, might not exist. In the world of causal set theory, space-time doesn't get infinitely close together, so there's no room for these singularities. And if there are no singularities, it challenges the idea of a Big Bang because, in this theory, the universe has always been here, and time has no real beginning. It's like a never-ending story. But here's the important thing to remember. We don't have any solid proof of this yet. We haven't actually found these tiny units of causation called causates, similar to how we've never found the tiny strings in string theory. However, the math behind causal set theory checks out, even if it's super complicated. Now let me try to explain some of the key concepts. Causal set theory is built on a mathematical idea called a partial order relation. It's like a way of describing events that have cause and effect relationships with each other. These events are connected in a certain order, like a chain of events. One of the rules of causal set theory is that this order can't have loops. Events can't cause each other in a circle. Another rule ensures that the structure isn't too crowded or too empty. There's much more to it, but that's the basic idea. Now, when we talk about these tiny pieces that make up space-time, causates, think of them as point events that carry information about their ordering. Some events happen before others, and some happen after. This ordering is what we call causal relationships. In causal set theory, everything is based on something called Lorentz geometry, which is a way of describing how light moves through space-time. It uses light cones to do this, like circles in Euclidean geometry. These light cones help us understand how particles behave at high energies and near black holes. So here's the big idea. Causal set theory doesn't need to explain singularities because it doesn't have them. It suggests that instead of a Big Bang, the universe could have always existed, with events occasionally creating bursts of energy and matter. Imagine these as random waves in an infinite ocean of space-time, but because these bursts can't reach each other due to the speed of light, we'd never know about them, creating a sort of steady-state multiverse. This is still a theoretical concept, and we haven't proven it yet. It's a fascinating idea in the world of physics, and researchers are still exploring its implications.